It's okay. Try to put your microphone.
Where's the clip?
Here, maybe in here.
But where's the clip? It's gone?
Yes, it's okay. It's okay.
But there used to be a clip
Your bell.
on the bell.
Rather than,
But what about the clip?
Here, maybe here. We try to maybe.
But it's lost?
Maybe here.
Et perdu?
Perdu.
Ah,
I don't know. I don't know why.
okay. Okay, I'll try. So you can still see it though.
So I'm giving away to the speakers a form which you're free not to sign or sign, which is about showing film lectures on the web.
Oh yeah, I don't know. That's
So
okay.
I would give it to you.
Okay. That's kind of nice to have them on the web.
It's kind of nice.
Yeah, it's nice to. Then people can go look at them, like
I
my
think
students,
so.
for example.
Yes, I think I have many emails asking.
No, I'm for it. I'm happy to do it on the web.
That's very good.
But they're where at this Institute Fourier, or who keeps them?
Yes.
And they keep past schools too, or so?
And they keep
The past school, or
past school, yeah, but it's the first time we're filming.
I see.
Past school, sometimes they've been published by a volume of Panorama et Synthèse or this kind of thing. Which we can still consider doing. I mean, it seems that people are writing more than what they initially said, but
there's a summer school every summer here.
yes. So it's usually on geometry-related things because it's a pure math department. Geometry people are the
So you
vast
propose
majority of
this topic.
Right. Or they told me if you want any funding. Anyway, yes. For example, I mean, last year it was number theorists, but they did it on arithmetic geometry and moduli of curves. So 3 years ago it was the same people of my team, we call it group, geometry, and it was on rational geometry with Alessio Corti again.
Oh, I see.
In between, there may be some differential geometry. Maybe 2 years ago, it was.
And now that Alessio's given up talking about oil.
But yes, exactly. I'm wondering if he's going to speak about that.
But the price is going up again, so it's a.
I think it was.
When it went up a lot, he spoke. He gave when at Pisa he gave 1 out of 4 of his lectures was just on oil. And then the price crashed, and he couldn't really say very much.
I will stop him too if he does that, because I think he's really not.
It's pretty hard to stop Alessio.
Yes. But,
He'll be happy to yell over you, I think.
Between me and him, we can do that. Okay, so let's start the second lecture of Rahul on stable quotients in relation to the block.
Okay, so I wanted to say a little bit about where I ended last time, which was 2 days ago. And it was already reviewed briefly in Carol's talk. So we had here the universal curve over mg, and the fiber product, the d fiber product, the universal curve over mg, and then the universal curve over that. And this has these sections, S1 to SD. And I use this to construct bundles on this fiber product. E goes to FD. And if I'm in this regime where D is greater than 2G minus 2, then we saw before this was an injection and there was a quotient. And the rank here was G. And the rank is D. And the rank of this last fellow is D minus G. So we had this relation Ck of Q is equal to 0 for K greater than D minus G. And so just so we start out slowly, remember that this was the Hodge bundle. So it has fiber H0 omega C, and this bundle has this fiber that also is in the talk, Carol's talk in the morning. Okay, so, and what we did last time was a long calculation about how to expand this Chern class and push it down, and it had this slightly anticlimactic end of getting nothing, all right? And so, and that was this pushing down Ck of Q for that range. This is a class that's 0, and we learned how to express in terms of kappas, and I said we got nothing. And the solution for that was we should do something a bit richer, which was also discussed both last time and also this morning, is we can multiply, since this class is already 0, we can multiply it by anything we want. And before we push it down, and there's various things we can multiply, but I wanted to give a solution for something. So here, we're going to multiply by a polynomial in these diagonal classes. So remember, these classes Dij are in, they're the various large diagonals. All right, so then I wanted to just start here by explaining what the solution and leave most of the calculation to you, because the technique's exactly the same as what I explained last time. So, and there's also several ways to do this. But we need to put these classes in to use this these kind of this kind of summation arguments we were discussing last time. We need to put these classes in a way that's democratic with respect to the labels of this fiber product. So the simplest way to do that is to look at insertions. So there's a D is kind of a overused variable here. I remind you that we already had Dij, that's the diagonal. We also had this delta I. This was the sum of the diagonals. D1I plus D2I. Di minus 1I. So now I'm having a delta. And this, so we'll have delta 2 is minus the sum of all Dij's. And delta 3 is plus the sum of all Dijk, where these indices are all different. So this is the biggest diagonal. This is the second biggest diagonal where 3 indices are the same. This is a sum over all distinct issues. So just, sum over all pairs here, all triples. So in particular, there's D choose 2 elements in this sum. Maybe I'm saying things too much. But D choose 2, D choose 3, and so on, with alternating sign. Okay. So then I want to tell you what this formula is for, and this is probably the most complicated formula just to write in these lectures, but it's something concrete and something that one has the possibility of studying, so I wanted to write it. So how to do this push forward where we have this class at 0 and we multiply against it a polynomial in these classes here. So delta 2 to the R1, delta 3 to the R2, so on. Delta L. All right, so it's this. So this is, as I said, and so at some level, it's very different from what we did last time, since it will give something non-zero, and it's more or less equivalent to the conjecture that Carroll wrote, the second conjecture that this should give everything. So in this way, it's very different. There's going to be lots of non-trivial relations here, but in the way, it's going to be very similar. And the analysis we did, it just is just the same to write down the formulas for the calculation of these. So I'm going to write that down now. All right, so remember last time there was E, and we had to know how to deal with the total Chern class of E dual, and nothing's changed here. That's the Bernoulli number expression. Then there's this FD, and we have to learn to deal with the total Chern class of FD, and this is what we did learn last time. Okay, so the new thing are these insertions we're putting in here. Delta 2, delta 3, these diagonal, these cutting classes, or these were called cutting classes before. And so the outcome of this is that last time the answers were all described in terms of a rather simple function. And this rather simple function last time was a function of 2 variables, t and x. And those variables, and this was the sum d. Okay, so this was the function last time, and now the function. So in words, when we include these cutting classes, actually everything is just the same, which is we change this function. And we make it a little bit bigger. So we add some variables, S1, S2, so all the S's. So if the interpretation of this T before was it treated dimension of the integrand x was the number of points, which was the D. And these S's will keep track of these insertions, delta 2, delta 3, and so on. So anyway, what is this function? It looks very similar as before, except it's a sum over sigma, the outside sum of this is over all partitions. And then we have the same sum over degree, the sum D, and then E stays as before. Negative 1 to the D. C to the D. And now comes the S's. They have to play some role here, and that's where these these cutting classes come, and they come like this. J1 to L, so sigma is a partition. L is the length of sigma. And then I have here D choose R J plus 1 S to the RJ. RJ factorial. So that's the function. It's a big function. So just to unpack it, what is sigma? Sigma is a partition. I can write sigma. One way to write a partition is 1 to a certain number of 1s, a certain number of 2s, and so on. This is not the length, actually. Sorry. Okay, so this is the formula. It looks scary, and it is a little bit scary, but it's not terrible. So we started with a very simple function, and we're giving this some kind of extension with these s variables. And then the theorem, which is maybe some kind of first evaluation of Faber's relations, is that if you want to exactly get these relations, you take the log. I mean, we've seen this now, this path several times, and it's just this hallmark of this Wick combinatorics. We take the log. Depends on sigma, t to the r, x to the d, s to the sigma is this way of putting sigma 1 to the r1, sigma 2 to the r2, and so on. So it's maybe not so worthwhile to think too much about this, but then I write this gamma as the Bernoulli number, the Bernoulli terms. So we'll be done with these formulas in a moment. And so here come the kappas. I think there was one. There's one TR. This is T. So here come the kappas. So this is, I said, this is just the exact parallels we did, several times now. And the equations, finally, the equations are the following. So this is the relations that come from Faber's original method, and they are, you take the exponential of minus gamma t to the r, x to the d, s to the sigma, and this equals 0. It equals 0 as long as your r is greater than minus g plus the size of sigma, and d is greater than 2g minus 2. And this relation is exactly that relation over there. That's the relation. This is the relation you get by that push forward. So yeah, so I mean that's sort of a long discussion of the formulas, but it's incredibly precise, and one can think about it, and it has some good points and some bad points. So it has this this particular form, which it inspired, as Carol said, inspired further guesses and progress in the subject, and it's somehow reasonably concrete. And it has some bad properties, which I want to discuss now a little bit. So what should I erase? What? Yeah, sorry. Where did I say? Oh, yeah, here. Okay.
There.
Yeah.
Delta 1, delta to the R1, delta to the R2, should that be delta L to the R minus 1?
Yes. Okay, very good. Oh no. So I was going to say now So I was going to say now some of the bad things, but I can't say it with this board covering it up, so I will leave it here. I'm sorry about this. You know, this expression here, and you know, this kind of mathematics is rather concrete mathematics. You have to, in some sense, love the formulas to get involved in this. But this expression I'm giving you for the relations is much more concrete than just saying the right-hand thing there. I mean, the right-hand thing is doing it just expresses the answer as some geometric intersection theory. This gives you the answer in terms of, you know, actual numbers. So in this sense, it's a much better expression than just that. So why do I say it's not optimal? It has some drawbacks, and one was already hinted at in Carol's lecture, is that suppose I want to expand these relations. So that means I pick my favorite genus, and I want to look in this tautological ring. So I pick some genus, and then I pick some codimension R. This relation, the way these are indexed, this R is this codimension. So I'll pick this. This will be fixed, and this will be fixed. And I want to find all the relations I can with this R and G. So what do? Well, what freedom do I have? Well, I get to pick D however I want, and this partition however I want. And this D has to be subject to this. But that's not a problem. There's a lot of numbers that are bigger than any particular number. So I have an infinite number of choices here. And then what about sigma? Well, once I pick this D, as long as I have some room here, so if R is greater than if I have some room here for sigma. I mean, sigma can't be incredibly big because I have to have this. So the sigma is not so much choice, but this D gives me infinite amount of choice. And so what this means, and this is a drawback in this expression here, is why this is a problem is it gives me infinitely many relations. So if I am trying to answer the question, even this most minor question about this is, you know, how many independent relations that are there, I can't answer it. I mean, I can't answer it without further thought. And as a matter of fact, we don't know how to answer that question. So this is a defect of this. It's a solution to some extent, but it's not full. It doesn't give somehow full understanding of even the relations that come from this particular construction. Okay, so that's the end of this discussion of Faber's original relations and their particular concrete expansion in terms of this Wick combinatorics. And as I said, this is kind of old stuff, and it's not the way the most recent advances forward. But I think it's a very nice place to start because you can understand the geometry immediately. And if you want to understand it, you can really just concentrate on how this intersection combinatorics works. And if you really want to work in the subject, it's very good to understand all the steps I said here. Like actually check this formula is right, correct the signs and whatever. It could be. Okay, so now we go forward, and there are some questions. And these questions are the question one, the most natural, is are these all the relations? This has to do with Faber's second conjecture. All the relations. A second question, which is maybe more, it's a slightly more concrete question in some sense, is can we solve these equations further? Can we solve those equations further? Which is to say, to have them in an even more concrete form. One that, for example, you might be able to actually calculate the dimension of this relation space. So, all right. So now I would like to repeat this proposal that Carol said. So this was, again, a long time ago, when, for example, the Western world still appeared to be solvent. And there was a proposal Carol wrote this morning, and I will write it again now, which can be viewed now in slightly different terms, but anyway, let's write it. So I want to write it in terms of these functions. So the first function is this a of t. And this function, as I said, usually when I talk about this function, really plays the starring role here. And the equational complexity of the talks will go down a little bit now. So, but as I said, at some point one has to learn to love the equations. So there's this function, and this function. So let's think about it for a moment. So I said this function in this proposal of relations of Faber and Zagier, this function plays really a starring role, and in some sense the whole proposal comes from just this function. And so let's think about it for a moment. It looks like almost like hypergeometric series. If you think about it slightly more, you realize it's a kind of a weird function because it has a radius of convergence 0. It's slightly unpleasant function. It's a formal series. So if you remember what was written in the morning, there was another function that came up. And the other function is this, which looks very similar. Oops. It looks incredibly similar, just as another term here, which I'm concentrating to get right. There. Okay. So that's the second function. And this function is not really so different. So they're related. The relation between this a and b is the following. If I write in the variable z, if I write this variable z is equal to t over 72, then the relation becomes minus 1/2 a plus za plus 6z squared dA dz is equal to 1/2 b. So this is the relation between a and b, and this is just to demonstrate really that b is not really a new actor here. It's just a. And in fact, when one studies these, this whole kind of differential algebra generated by a will play a role. B is the first time something comes. But one should really think about that the proposal is about this one function a. And it's somehow a philosophical question, why is this function a? I mean, where does this come from? I mean, well, maybe said differently, does it arise in anywhere else in mathematics? Okay, so then the actual proposal for equations. The actual proposal for equations, and as I said, this was already in the morning talk, but perhaps you don't remember exactly what it was, so I write it down here. We define a function in many fewer variables. I mean, as I said, things become simpler now. This t is one variable. This is some set of variables, and it's a very peculiar set. It's indexed by numbers. In fact, all numbers except for those, so except for 2 mod 3. So we look at an index set indexed by all integers that are not 2 mod 3. And then we just repeat here what was written in the morning, except I write it here. So here I put all the things that are 0 mod 3. And this is times A. And then I put all the things that are 1 mod 3. Oh, we got it right. 7 times B. So this is not so hard to think about. It's not so bad to think about when you erase all those factorials. All right, so this is the function that Faber and Zagier produce, and then we do this same formalism that we've seen now several times. We take its log. I'm sorry for writing this again and again, but maybe after repeatedly writing it, you'll understand completely. So these are all overall partition sigma. And then we write gamma to be the sum over all partitions, the sum over R, 0 to infinity, CR gamma. And then here comes the kappa, because this whole subject is about the kappa, C to the R, P to the sigma. And finally, we come to this proposal. These are the FZ relations, and they are and so the statement is in R and G, the relation x minus gamma TR P to the sigma equal to 0. This holds. And then there's the conditions. Ta-da. So the very peculiar conditions, when you first see them, G minus 1 plus sigma is less than 3R. And then the even more odd condition is G is congruent to G is congruent to R plus the size of sigma plus 1 mod 2. Okay, so we're going to, so Carroll told the story about these equations. They were proposed. They were somehow miraculously extracted from looking at the data, and they were shown in the past to hold in the Gornstein quotient, and shown more recently by the stable quotient methods I'll talk about to actually hold in the ring. And these equations are really nice equations, as opposed to the theorem I wrote before. So they have a certain finiteness property. So let's discuss some properties of these equations. So if we do this, if we have this idea that I want to look at fixed R and fixed G, and I want to see how many of the FZ relations there are, this is now, it's a completely finite problem, because if R and G are fixed, then I only have finitely many partitions to look at. So it means it's only the linear split. We're only given here a finite number of relations. Right? So this is this kind of completely solved form we want. So a statement. So this is the first good property, is that there's a finiteness to it. Maybe explicit finiteness is better. I mean, all systems are eventually finite. Okay, so something else that's a very striking quality of these equations is this mod 2 property. And so this can be said in the following way. Suppose I have one of these equations. I'm here in R and G, and I satisfy these inequalities, and I find an equation. Then I claim that that's same, so let's call that equation E. E equals 0, one of the FZ relations. Then I claim that I can consider that equation in mg minus 2. That's a strange thing to do, but I can just take the same equation and consider g minus 2. And now I look what happens here. Are these inequalities satisfied? Well, I've kept everything the same here, and I've lowered g, so this one's still satisfied. And here, I've changed g by something mod 2, so it's still satisfied. So one very peculiar property of these equations is that if I have an equation for a particular place, it holds for lower genus by 2. And yeah, so I defy you to figure out why such a thing, why such a property should hold about mg. And there's so this is, all right, so second property. So the third property, this is a property that has come, I think that something that was has only come to light recently. I mean, recently in the context of the 20 years of study of this, is that I think it's fair to say this, is that no one, at least to my knowledge, has found a relation in here which is not in the linear span of the FC. Okay? So if this last statement were not true, meaning that if there were known methods to produce other equations, then I think it'd be fair to say this class of equations would be less interesting. It'd be some subset of the possible equations. And probably the belief that this was true, I think that for a long time Carroll presented the two conjectures. The first is the Gornstein conjecture. And the first time he told me about FZ, he also told me understood that it does not imply the Gornstein conjecture, and therefore probably there's more relations if you believe the Gornstein conjecture. And to that extent, if you believe there's other relations, then why study these particular ones? But in fact, further computations by Carroll mostly have shown that so this statement is true. There haven't been any ones found. So a conjecture which was not quite stated, I think, in Carroll's talk, and probably the subject doesn't need more conjectures, so I won't state it as a conjecture. But certainly the data at the moment, and it's a very interesting time for the subject, because some questions that weren't anticipated have really now come to the fore. So a question, which I think really important question. Is or are? Is. Are the FC relations all, I mean, the ideal generated, etc., linear span of FC, all relations, are the FC, all relations among kappa classes? Okay, so we'd very much like to know the answer to this question. And you could also ask, for example, are the FC relations equal to the relations of the first theorem by Carroll's original construction, etc.? We'd like to know the answer to all those questions. But we don't know the answer to almost any of those questions. There's exactly one question we know the answer to, which I will explain about these relations in a second. But we don't really know the answers to any of these questions. And yeah, so if it is the case that these are all the relations, or they give all the relations that were explained in the first theorem of the lecture, it gives this kind of completely, let's say, some kind of completely solved form for those relations. It certainly could be. Now, if something that a person could try to think about, as I gave an explicit, it's been erased now, but its shadow is somewhere here. There was a theorem with this very large function and this explicit outcome of the original relations, Carroll's original, which relied just on some very elementary algebraic geometry of curves. One could try to prove mathematically they're equivalent to these FC relations. And this is just a question. Actually, sometimes has nothing to do with geometry. Can you do it? That kind of stuff is pretty hard. But if anybody does that, we're very interested in those kind of.
Is it known that these equations imply the proportionality in highest rank?
Actually, yeah. So that has not been formally proved, but
But it's a conjecture.
I mean, I don't know. Okay, I don't know what your view on this thing is. That stuff hasn't been proved, but in practice, it's going to be true.
How do you reconcile this question with what Carl said in the previous one, that never expecting the FC relations to be all relations?
So this is a good question. There's two places you can view FC. Because after all, FCs are this is just some way of getting polynomials among the kappa classes, right? I mean, here I'm getting just some, FZ is a method of getting some polynomials among the kappa classes. So you can view FZ as specifying a relation in two types of rings. So one of them, and now I'm struggling to remember Carol's notation for the Gornstein quotient, R bar. So this was what Carol called the Gornstein quotient. And this is the actual tautological ring. And the actual tautological ring surjects upon the Gornstein quotient. Now, if the actual tautological ring is Gornstein, then this is an isomorphism. All right? So the thing that is clear, Carol mentioned it, I mention it now, and you don't have to believe me. You can do it yourself. It's elementary assertion, is that in the Gornstein quotient, FZ can't give all relations. Because the Gornstein quotient requires a certain growth in the number of relations to get the bottom half of the diamond. And FC doesn't provide this growth. So this is why at the beginning, and Carol said it, you don't expect FC. It's better to say you don't. FZ cannot give all the relations in the Gornstein quotient. Well, it's a question. Answers might be incompatible. Like answer could be yes. FC gives all relations. All relations. So if the answer is yes, FG gives all relations, then this implies that Gornstein conjecture is false. But if the answer is no, FC does not give all relations, then the Gornstein conjecture could still be true. Right? So if yes, then the Gornstein conjecture is false. Okay, are there more questions? But especially since I gave the another reason somehow pedagogically it's good to give some kind of expansion of actual geometric relations before I give the FC relations, you can appreciate how slick and elegant the FG relations are. I mean, think about the first things I wrote on the board. This is just an infinitely better presentation. It's a really nice thing, the FC, and the history of the accidents behind it are kind of surprising. So I want to now explain how some of the geometry. So this was a lot. I mean, this lecture today was almost geometry free. So I want to now go back to geometry and explain how to prove the FC relations, at least to know they're true, which means that to say that the FC relations actually hold here. And even here, I should say. So when I say so actually what is proven is the FC relations hold in the strongest possible sense. So one strengthening, which I said Carol and Donzaghi already knew they held here. So we prove that they hold in this tautological ring. And there's two ways to think about the tautological ring. One can think about this, and you should use different letters for it, but we don't have too many letters on the board. One can think about it in cohomology, or you can think about it in Chow. So we prove, so this is in the notes or with this Pixton. I'll say a little bit about this. So it's proven actually to hold in algebraic cycles. And an even stronger statement is true, is that after all, these are relations on a non-compact space. You could wonder what what's happening in the compactification. And the strongest statement the strongest simple statement one can expect is also true. Is that if I take an FC relation which is called E, these kappas. So this is some equation that's 0 in R. So this means I pick this sigma. Maybe I should put sigma in the notation. I pick this sigma. I'm sorry, I haven't. G, R, sigma. So if I take one of these FC relations here, you can wonder, what does this mean? We're talking about cycle classes. And the strongest way it's true, and it comes out in the proof, is that actually this is equal to a class, or maybe I should say it. So what's the best way to say it? That this is equal to a class alpha, where alpha lies in the tautological ring of the boundary. So if we look at mg here, here's mg, and then there's the boundary. It's hard to draw this. That's the boundary of mg. And if I look at this kappa and mg bar, actually we show they're actually tautological on the boundary. It's equal to a class tautological on the boundary, which certainly means they're 0 when I look at when I restrict to the interior. But this the method shows that they actually live at tautological class on the boundary. Okay. So that's the way they're true. And so now we maybe forget all about this now, and I want to explain how it is that they're proven. And this requires, to be fortunate in many ways. To even come to this point requires this amazing luck that Carol Faber and Don Zagier were able to write down the FC relations, which is some kind of real triumph. Then after that, one needs to have some kind of further luck of finding some geometry which will lead to some geometric equations. And I already discussed Carol's original ones, and Carol discussed several already in his lecture. And one has a lot of freedom. You can pick your geometries that lie over mg and try to write down relations. And to be able to prove some theorem like this, you have to just be able to solve the equations and really solve them all the way. Explicitly evaluate them. So one has to keep looking for that geometry. And the place where we found is a moduli space of stable quotients. And in fact, part of the whole motivation of defining and studying stable quotients was precisely for the purpose of studying relations in the moduli of curves. So let me say something about this. So while I'm making some philosophical remarks, let me make some more. So here's mg. To get relations among kappa classes, almost by nature, you study moduli spaces above or sitting above mg, because kappa classes themselves are defined by moduli space that's above. So we discussed Carol's relations, and that was this space. So there's this geometry, and it's really maybe the first geometry that one thinks about, the fiber product of CD. So this is the first geometry. So tomorrow I will talk about another geometry that people have studied a lot, especially in the last 20, 30 years, is we can think about the moduli of rank 2 bundles. And this as the curve varies, you can consider this moduli space of rank 2 bundles on the curves, and that varies. And this comes with a lot of special geometry, in particular this Hitchin connection on the Verlinde bundles, and we'll use that to get some relations. We don't know how to solve those yet. But what's going to come here to prove the theorem at hand is a different moduli space. So the actual moduli space is moduli space Q, G of stable quotient. This moduli space, which I will define, and it's relatively new, although in some sense it should have been studied some time ago. It's a cousin of another very well-known moduli space, which is the moduli space of stable maps to P1. So this moduli space of stable maps to P1 has been coming in and out of the lectures here. So it's kind of a cousin. And in fact, I had attempted many times, and worked with Carol in the past also, to use this moduli space of stable maps to P1 to make relations in MG. Maybe I should take the bar off just to make relations in MG. And there were some successes there, and there were some difficulties. And as I said, these moduli spaces, you'll see, they're cousins. And in a way, this is a much better behaved, much more tailored to the precise narrow problem of looking at moduli, of looking at relations there. It somehow integrates out a lot of complexity here, so you don't have to do it by hand. But, okay, so this is one philosophical picture, is that if you want to make relations in the moduli space of curves, you're almost always, when you start thinking about it, thinking about some geometry that sits over MG that you know something special about. Right? So that's the one philosophical remark. The second philosophical remark I wanted to say, since there's been a lot of discussion in these lectures in the school about integration, I wanted to say how this enterprise sits in with that, because it's a quite natural question to ask. So we've seen things like mg bar and some integrals of the psi classes. So this appeared in several people's talks. And in at least, well, I don't know, perhaps other people's talks, we had some things which are related to the moduli space of a compact type. And these are integrals that look like this chalk is crumbling on. So these are integrals that, the analogous thing to here, I don't say so much about this, but this is just some motivation. So they appeared in Molazi's talk on the lambda G formula. So this mg bar is a space that has been defined as you look at curves and compactification by nodal curves. Compact type sits inside as an open set, and this is curves with the precise thing to say is their dual graph has no loops. So I'll just say curves with no loops. And I'll draw a picture. So this is an element here, could be an arbitrary nodal curve, and this is a loop. So it may or may not have a loop. And the curves here are the ones that are allowed to have nodes, but no loops. Another way to say it is that every node is a separating node. It moves. So it turns out when one studies this geometry for a while, you realize that the analog of this is this. And what we're talking about here is mg, which is even smaller. This says that you're allowed to have nodes, but they must be disconnecting. And mg is you're inside, but you're not even allowed to have any nodes at all. And the analog of the integrals that this set of, in a very precise sense, the analog is this. Lambda g minus 1. I don't explain all of this, just so this is some kind of roadmap for students who might have seen these various aspects in different talks. This is in a very precise sense the analog of those. And the formulas for this formula has come up, at least constrained by the Virasara constraints in various talks. And this formula is an almost explicit closed formula. This has come up in a different guise as Faber's original proportionality conjecture. So this question about these numbers are really at the bottom of this ring. This number sits at, if we look at this tautological ring, R star mg, this tautological ring has a top, that's R0, and has a bottom. This was discussed in talk in the morning, Rg minus 2. And these kind of the story about the relations and how they live in this tautological ring are all about this piece right here. And the discussion of what's happening in these lectures about relations among the kappa classes, the FZ relations, and the Gornstein stuff, is about what's happening really in the bulk of this ring. And there's been, I think, general movement away that what happens in what has been the methods from topological string theory, etc., have been very effective at telling us what to expect. I'm starting with Witten's paper in 1990 about what to expect, how these integrals behave, and that's always about what's happening really at the bottom. And what happens in the middle is this kind of new territory. And this is how to think about the relations. Okay, so maybe that's enough philosophy. And it's certainly easier to talk about than all those equations. All right, so now I want to say something about the stable quotients. I will say some more tomorrow, and I'll also say a little bit about the Verlinde flatness. But wait, before I say that, I just erased this question. This question, which was here, are the FZ relations all relations? There's one regime where the answer is known. The answer to that question, yes. Well, let me write it. Yes, FZ is all relations for genus less than or equal to 23. This doesn't quite this does not contradict the Gornstein. So if this statement is true, the second statement is if FZ is all relations for g equals 24, then R star 24 is not Gornstein. So these are two true statements. The first is unconditional. This is the fact that we know this is by a consistent hard work by Carol Faber and this computational aspect of how these relations work for many years. And this is a conditional statement, but it's about, it goes to the heart. The heart of the matter is genus 24, about the conflict between these two things. Okay, so there are more questions, or any questions at all? All right, so now we come to this moduli space of stable quotients. And yeah. All right, so I said, so now we're going to start with some geometry now, and really everything else I said in this lecture is not related to what I'm going to say for the remainder. So we start with C is a connected nodal curve. So I will use the terminology, and I don't think this precisely agrees with what Farkas wrote, but it's been a long time since his talk, so we can. So this is quasi-stable. Okay. And it has this curve and it has a genus. And so the picture of this curve is just like this. So there's no stability condition imposed. It's just connected and it's nodal. All right. And so now we're going to consider on this a quotient sequence. A quotient. What's a quotient? I mean, there's many ways to play this. So let's consider this case where I fix an R and an N, and I consider quotients that look like that. All right, and so this is when I write C to the n tensor OC. This is the trivial bundle. This is n copies of the trivial bundle, and this is a quotient. So this is a quotient on C. And now I'm going to tell you what is quasi-stability of a quotient. Of a quotient. Well, so let me just say precisely. When I say a quotient, I mean C together with this data. So this is a quotient. I take a curve C together with a quotient. Right? The quasi-stability of this data is that C has to be quasi-stable, which is just to say it's a connected nodal curve. And then there's a condition, which is the more interesting one, on the quotient. And the condition is that Q is locally free at the nodes of C. So this is a meaningful condition, right? So so if I have this data of a quasi-stable quotient, it's saying something simple. I have a nodal curve, and I have this quotient sequence, and this Q is so if I draw this picture of Q, so here's my curve, and now I draw it like an algebraic geometer, and Q is some sheaf, lives here, and on points that are not nodes of C, like in here, then this sheaf can have torsion. It can be, it can have torsion. I don't really constrain what happens to it. But every time there's a node, which is of course a very sensitive point for C, and the node, I insist this Q is locally free. All right. So one of the consequences of this quasi-stable condition is so there's two elementary consequences. The first is, I already hinted at this, that a sheaf might have a torsion. Well, a sheaf has a torsion part, and the support of this torsion part. So this is the torsion sheaf. So a sheaf has a torsion sheaf, and it's a torsion part, and the support of this torsion sheaf lies in the non-singular locus. Right? I mean, it's just another way of saying what I said before. And the second, and this is maybe a more important claim, is that S is locally free. I explain this in a second. What is S? There's no S on the board, but if I have a quotient, I can always take its. I didn't write it, so you didn't concentrate on it, but because it's not more data, of course. If I take a quotient, there's always a kernel. So I can think of a quotient as actually the whole data. And if I satisfy this quasi-stability condition, you can check by your algebra that actually S is locally free at the free everywhere. Q is not locally free. I've only asked it to be locally free at the nodes. It might be not locally free elsewhere. But so you could say, well, how come this the local freeness, the failure of Q to be locally free elsewhere, how come it doesn't screw up S? It's because S is it's a curve, the smooth point of a curve. So this is some kind of basic algebraic geometry. All right. Where's good. I didn't tell you what R is because I hadn't have S on the board. R is the rank of S. So I could say it the other way, that Q is n minus R. All right, so I'm going slowly here so everyone understands. There's nothing much in these definitions. We have a nodal curve, we have a quotient sequence, and then in a sense, if there's something new here, you should concentrate on this quasi-stability condition, which says that this Q can't be. It has to be locally free at the nodes. That's kind of the crucial. A crucial non-trivial assumption here. Okay, so now we discuss stability. This was only quasi-stability. We're only quasi-stable. So quasi, yeah. We haven't discussed stability yet. I know what you're asking. Yeah, as I said, yes. You know, it's like if you talk about a Deligne-Mumford stable curve, before you impose stability, you can have unlimited chains of P1. I told you it didn't agree with your notation. So we now discuss stability. And after this, Gavi will be happier, I think.
You want to allow these chains of P1s to keep this to have torsion up away from the nodes, right?
Yes.
And in order to do that, do you have to allow arbitrary long chains? Or
Yes, yeah, arbitrary long
or
chains.
you can bound it by the rank?
No, you can't bound it by the rank. You'll be able to bound it by the degree.
Right.
Yeah, you will be able to, yes. I mean, at the end of the day, it'll be a moduli space of finite type, so the discrete invariance will allow you to bound how many P1s will come.
Do you mean unbounded finite chains or infinite chains of P1s?
There's no infinite chains of P1s.
No.
I don't consider algebraic varieties with infinite numbers of components. All right, so let's discuss stability. But this is a kind of a confusing interlude, so maybe if we should just delete that conversation. So if I have a curve that's quasi-stable, on it there is the dualizing sheaf, the sheaf of differentials for nodal curves. So you have to know what that means, and I hope you know what it means because it's been in every lecture in this school, I think. So, what is stability? So Deligne-Mumford stability. This is equivalent to saying that this is ample. Right? So this is a way to write stability for a curve. It's a quasi-stable curve with the dualizing sheaf ample. Right? So now we come to a quasi-stable quotient. So if we go back to this confusing part, this is the thing that controls the bubbles of P1. So now we take the quasi-stable quotient. So this is the data of C in that sequence. That's a quasi-stable quotient. And now we have to discuss stability. So this is stability. This is the stability. A quasi-stable quotient is defined to be stable is equivalent to to an assertion that's exactly like this, except with a slight twist. Now I write it here. I take omega c, which I still have because underlying curve is quasi-stable, and I tensor it by a line bundle. Now what line bundle do I tensor it by? Well, in this sequence, what objects are bundles? Well, I said this may not be a bundle. This is a bundle. It's a trivial bundle. It's hard to get much action from him. And then S is a bundle. But S is a negative bundle because it's inside here. So I can take, I want a line bundle, so I can take the determinant of S dual. This is now a positive line bundle. Well, at least it's not a negative one. And I tensor it up to the epsilon. So its stability is equivalent to this fellow, which is a little bit of a strange object to think about if you've never done it before, is ample for all epsilon greater than 0. Okay, so that's the statement. And now since it's a somehow peculiar condition, we discuss it a little bit. Right. But if you're a sufficiently well-tooled moduli theorist, then you should just be able to take this and then finish the construction of this space. But let me tell you what this means in practice. So let's suppose I have my curve C. Maybe it's a genus 2 curve, and it has has a rational tail here, P1. So it's a genus 2 with P1. And now I ask myself, can such a, and then I have some quotient sequence on it. Right? And now I ask myself, can this be stable? Stable quotient. Now I know this underlying curve is not Deligne-Mumford stable, all right? But that doesn't disqualify it from being a stable quotient. It is quasi-stable. So to figure out whether this is a stable quotient, I have to figure out whether this omega c tensor, the determinant here, so let me write it as determinant for fun. Dual. I have to decide whether this can be ample. Is it possible this could be ample? Well, so I need to know what is the degree of omega c here. The degree of omega c here is something positive. The degree of omega c here is -1. Right? This is what violates, this is how this curve violates Deligne-Mumford stability. The dualizing sheaf has degree -1. The dualizing sheaf has degree -2 on P1, and then it gets a little bit of help from this point, but it gets to -1. So this has degree -1, and now S could be anything. S could be really positive. It could be, some like O to the 30 million or something like that. It could be a really positive guy, but it can't fight that -1 because it has to be positive for any epsilon. So the answer is such a thing can never be a stable quotient. All right. So this is actually one of the this little calculation, this little geometry shows a little bit about why the stable quotients among all the various geometries to construct relations, why I like them. Because there's this suppression of bubbles of P1. You can't, in modular space of stable maps, which I think were defined, perhaps, right? No, I don't know. Well, in modular space of stable maps, which is, as I said, somewhat similar to this, one knows that you can have domain curves with some arbitrary growth of rational curves that come out. You could have some extremely complicated tree that comes out, as long as you support it with various degrees of your map. This cannot happen in stable quotients. You can't, no matter how much degree you try to put on this P1, it's suppressed. And so I view this as some kind of like chemotherapy or something like that. That it somehow prevents these things from growing, the stability conditions. And it's of enormous help, because when one does these, when one actually tries to evaluate relations, a lot of time is spent understanding this kind of tree summation. And the stable quotient somehow does that for you in this suppression method, this kind of tumor growth method, suppression. Okay, so what? So what can happen? I told you what can't happen. What can happen is the following. If I have a stable quotient that looks like this, a curve that looks like this. This is some positive, and here's a P1. All right? So if this is the underlying curve for my stable quotient, now what is the degree of omega c? Well, one knows the degree of omega c is positive here, and it's 0 here. Which would still disqualify it for Deligne-Mumford stability, because you need to be positive for Deligne-Mumford stability. But this is a Deligne-Mumford unstable curve. But so could it be an underlying curve for a stable quotient? And the answer is yes, it could, because I need a stable quotient. I need a stable quotient. Since this is 0, it can be ample. But this factor can push it over the edge. It can make it ample for every positive epsilon, as long as the determinant is positive. Right? So this can be, there can be a stable quotient on this. But the price is the restriction of S to this has to have at least degree 1. So this answers Gavi's question, that if I have, so in this problem, there's going to be a modular space of stable quotients. There's the genus, and it's suggestive to write it this way. Rn. That's the rank of S, that's n. And there's a degree, and what's the degree? The degree is, well, minus the degree is the degree of S. So there's a moduli space of stable quotients that parameterize, it's best to put it this way, that parameterize stable quotients with the fixed genus, the R and the N, as I said. This is the dimension of this space. And D, the final thing is the degree, and that's the minus the degree of S. So there'll be a moduli space, I'll say this in a moment. But this degree will tell you how many bubbles like this you can have, because every time you have a bubble, you have to pay for it by at least 1 degree. Is that clear? So, okay, so the upshot of this discussion is these stable quotients allow the curve to bubble more than stable curves, but not much more. All you can do is put in chains in between the nodes. You can't have these growths that come out. All you can have is some kind of chains in between the nodes. So the theorem is that there's a moduli space Q R D. So this is the moduli space of stable quotients with these discrete invariants. And this is a proper DM stack. And so this was constructed in a paper I wrote with Alina, Marian, and Dragos. And yeah. So there's a long paper in the archive that has the details of the construction, etc. And so it's, yeah. So there's some things to be checked here. We're not going to discuss it now.
Do you mean that it depends on a point with the Grassmannian?
No, yeah, I'll say this in a moment. That's just a notation, and it's to remind you that its cousin is this space. And the relationship between stable quotients and the moduli space of stable maps to Grassmannian has been explicated by Yokonobu Toda. His paper is also on the archive. But its cousin is this space. This is the moduli space of stable maps to Grassmannian. And why do they say they're cousins? Because both contain, as what one might think is the principal locus. See, if you have a curve, let's say it doesn't break. It's just actually a smooth curve. And if I have a quotient, and I happen to be that this quotient is locally free everywhere, then this is the same data as the map from the curve of the Grassmannian. And exactly this Grassmannian of degree d. So there's an open locus in both these, not necessarily dense, but there's an open locus in both these spaces, which is the classical space of smooth genus G maps to the Grassmannian. That's why I use the terminology. Of course, I could just erase it and just put these numbers, but it's nice to, it's easier to remember. So, in fact, okay, so, and I mean, this property was crucial in its selection for the study of these relations in MG. I mean, there were a number of criteria that I wanted, well, I hoped for. One was this kind of tumor suppression, because this is really important because it simplifies the analysis really considerably. The second is I wanted it to have a virtual class. So this is what I will say now. So one of the very good things about this space is this deformation theory in the virtual class, and this was not maybe discussed too much in this school. It might be a little bit late, both in the week and in the day, to discuss it. I'll say so. It is a basic fact, and in some sense, one of the most basic, most important aspects of this moduli space of stable maps to anybody, to any non-singular variety X, is that it carries a virtual fundamental class. And I give you the most brief indication of why that's true is that its deformation theory is controlled by two groups. So if I have an actual map from a curve to some smooth algebraic variety, if I wanted to know how to deform the map, say by keeping the curve fixed, that's how you deform a map. This is in more or less any geometry. If I actually have how to deform a map is you pull back the tangent bundle and you take a section, because that tells you, so to speak, which way you're about to go at every point. And so this is the deformation space in algebraic geometry in particular, and then it has an obstruction space. The meaning of this is much more mysterious, and I'm surely not going to explicate it now. So it has an obstruction space which tells you in some sense what deformations are permissible, at least the first order. And it's a basic fact that in this deformation obstruction theory there's no more groups. And this is a starting point, requires a lot of work, but an outcome of all of this is a construction of the virtual class. And so one can find treatments of this by Berend and Fentecchi and Li and Tian, and well, you can look. Now, how does this work for stable quotients? So this stable quotient is not any x there. Right now, I mean, various authors have pursued the construction in other and more generalities for toric varieties, for GIT quotients, etc. But we don't need all of this right now, so we just look at this. So look at this modular space of stable quotient, just as I discussed. And now we can ask, does it have a virtual fundamental class? And the answer is yes. And this, to make this answer yes, was one of the motivations, and it was really a completely clear motivation of this locally free condition. It's precisely what motivated that condition. Why is that? Is that the deformation theory, if I have, so this is now some aspect of basic algebraic geometry. If I have a quotient, this is like an element in Grothendieck's quote scheme. And what is a deformation space? This has been known for a long time in algebraic geometry. The deformation space of such a thing is x0 SQ. x0 is Hom. It's probably less scary if I write Hom, but I'll just write x0 anyway. That's how to deform a quotient. And almost everyone who studied geometry secretly knows this. The simplest version of a quotient is a subspace of a vector space that gives a point in the Grassmannian. And this says the tangent space of the Grassmannian is the map from the subspace to the quotient space, which everyone who studied the Grassmannian knows or should know, or will know soon. So, and the obstructions in this are x1 of S, and then there could be higher obstructions. Oh, I should say, why is it there were no higher obstructions here? One simple-minded way, which is somehow decisive, is that we're actually on a curve, and the curve does not have higher sheaf cohomology for coherent sheaves. This is H0, H1, and there's no H2 any coherent sheaf on an algebraic curve. So what happens here? x2. So can I say so boldly that x2 is always 0? And the answer is no. x2 is not cohomology. x2 can be non-zero if you're in bad enough situation. But here we have that S, and this was, I said, really what motivated the definition for that local freeness that Q implied S is locally free. For something locally free, and it's a pity that's in the corner of the board here. Okay, maybe I'll elevate it. Over here. Because it's somehow basic for the definition of motivation. Is that if I'm looking at x2 of SQ, so using now this, you really uses the definition of stable quotients, not always true, def of stable quotients, def of stability. This implies S is locally free. If S is locally free, then I can move it over in the X. This is a property of X when S is locally free. Now this is another property of X. This is H2. So that's 0. So once again, we're happy we can use the H2 vanishing on the curve, but it's because this S is locally free. So we wanted, as I said, one of the motivations to have this virtual class, you need to have this behavior over the boundary that keeps the subsheaf locally free. But once you do that, then you get a virtual class. So the theorem here is that not only is this space, modular space of stable quotients proper to Riemann-Mumford stack, but it's with a perfect obstruction theory, whatever that is, which leads to a virtual class. And this whole theory is some kind of cousin of stable maps. And other people have bumped into it in terms. There's this movement in algebraic geometry about gauge Gromov-Witten theory, and people there like this construction because it fits into some of their goals. Okay, so I want to say something now about this. So in the case at hand, which now we come back to the point of all of this, which was to show you this geometric situation and how to prove this, how to prove the FC relations hold. We're going to use a very simple case, and it's not going to be a big surprise which case. For this Grossmannian Rn, we're going to use the Grossmannian 1, 2, simplest thing possible, which is something like P1. So we're going to actually use this stable quotients. I'll write as P1 degree D. And this is the one that's the cousin of stable maps, P1 degree D. And if you calculate the virtual dimension, how do you calculate the virtual dimension? Well, in stable maps, you take h naught minus h1, and here you take x naught minus x1, and you find that the virtual dimension of this is 2g plus 2d minus 2, which is no accident. This is the virtual dimension of this. And no. So we are going to use the geometry of this space to find relations. And I'll stop in a moment, but I'll give you a hint of how this is going to work and why it's so much better for this purpose than stable maps, which is, of course, a space I like very much. So it's been known for a long time that one can compute integrals effectively against the virtual class in these geometries by using the symmetry of the space, which is the basic C star. And I think this already came up in Zvankin's talk. If you have P1, it has a 0 and an infinity, and it has some action of C star that fix 0 and infinity. This was discussed, indeed. And this symmetry is extremely important in studying the integration theory of this. It's kind of decisive. And we can use it in both cases. But the difference between these spaces is the complexity of the fixed points. So, so we can ask, what are the C star fixed points? And so I just kind of draw a picture now. So the first case is for stable maps. And this is a very familiar picture for anyone who studied this before, and I try to draw it. So now I draw P1 like the way Farkas said he draws P1. Although it ends here. Maybe I should draw it like this. All right? And so how do I get a stable map? I'm not going to draw it that way. I'll draw it this way. So how do I get a stable map that's fixed? The stable map cannot do anything interesting in the middle, because then, as I rotate this space by C star, then it'd have to do something interesting over the whole thing, and you can't be interesting over the whole thing. That's impossible. So everything interesting has to happen over 0 infinity. So this means there might be higher genus components. They're crushed. And then what can happen in the middle, where there has to be these Galois covers? And this must have occurred earlier in the school. There are these Z goes to, there are these Galois covers. They look like cigars in this picture. It's very nice to look at them. Like, well, this is my attempt to explain what happens. You have what can happen for the stable map to be C star fixed. You take any complicated Riemann surface, you map it to a point, and then you have these Galois cover cigars that come out. And then using these rules, you can be as complicated as you want. You can have as many, as long as your genus and degree, as long as you can afford to pay, you can have more and more of these components go back and forth. And this graph doesn't have to be a tree. It can have loops. It can just be anything. Basically, it's any bivalent graph with some decorations. And this has been written in many, many papers. If that's confusing, look at the papers. So then what happens in stable quotients? And now, this is the last thing I'll say, and we can just concentrate a little bit and see what happens. Let me say something that's maybe first here. So this is what I said was the fixed point locus in mg bar. You might say, well, we're really interested in mg. So does that simplify the fixed point locus? And it does a little bit. It says that if we're not interested in any curves that map to the boundary of mg, then it does simplify this picture. It means that there's some place where it gains all its genus, and then everybody else is just a bunch of genus 0 things. So this simplifies a certain aspect of the discussion of the fixed point loci are. That at some point there's a genus mapped down, then there's these complicated trees of genus 0 things that come up. Okay, because that's actually relevant. So the thing that's very simple is this question: what are the C star fixed points of this space, the stable quotient space, P1 degree D, with so over mg, so no curves that are broken over mg. And so the answer is, okay, let's see. If I look at my curve, and here's the stable quotient over, it's going to 2 copies here. Okay, this is a rank 1 subbundle. I mean, so this is rank 1. This is rank 2. And this is degree minus D. All right, and the C star action is moving this. There's a C2 here, and the C star action is moving that C2. So how could I possibly be fixed? Again, this is this kind of interesting analysis. Is that if I look at S going to C2. C2 has these 2 coordinates. And could S be over a particular fiber? S can't be non-trivial in both of them. Because if S were non-trivial in both of them, then you could use a C star and exhaust the whole C2. And that would be a rank 2 fiber of S. But S is only rank 1. So that means S has to live in one or the other. So what happens is to be C star fixed, something very simple has to happen. S has to live entirely in one factor. Write it like this. And the quotient, let me say, S has to live entirely in one factor or the other. What does that mean? What does it mean if S lives in one factor? If S lives in one factor, that means S is the ideal of some points. In fact, it's exactly D points. So the answer to this question is, what are the fixed points over C star? There's actually 2 fixed loci. This 2 is very important. This 2 is the mod 2 phenomenon that occurs in the FZ relations. And so there's this explanation of it. There's 2 fixed points, and those fixed points are both C to the D over mg. They're both this. They're both C to the D. Because I said the fixed point S has to lie inside one of the factors. That means it's an ideal sheaf on one factor. And its ideal sheaf is just D points. So this is wrong. Sim D. D unordered points. Right? So we haven't discussed this space, but it's just the quotient of CD by SD. So the fixed point locus of the stable quotient is exactly 2 copies of Sim D. In this picture, what those 2 copies are is you should think about one of them lives over this 0 and one lives over infinity. It's just 2 copies of sim d. So there's 2 copies of sim d, which is of course, all our constructions of this kappa geometry is related to things like sim d and the fiber product of sim d. So we're very happy to recognize fixed point loci are just exactly 2 copies of sim d. And that replaces this, this kind of graph sums that come out here. Now, it is the case that I believe that if you take the stable maps geometry and if you're good enough at dealing with the complexities graph sums, it should more or less be equivalent. But as we've seen, there's going to be a fair amount of digestion in the equation, and it's good to start as easily as possible, so we're going to start here. Okay, so I'll stop. Yeah. Yeah, it may be. So this is a question if there is that. Yeah. So if it's the case that fz is all relations, then there's no money to be made. Period. Right? Because we're going to find them all here. If they fail to be all relations, then they're in principle one should start looking. You could certainly do it. You can look at others, but yeah. I have